So in part 3 of my little video series here, okay, I'm now going to reintroduce the IO that we were interested in calculating. And in the end, using our complex numbers, we ended up with a solution where IO is equal to 2.5 plus 1.5 J amperes. And again, I just ran out of space. Okay. So we get our IO is equal to, we got 2.5 plus 1.5 J. Okay. And then we wrote that in phasor form. It's like, what was it? It was like 2.91 angle of minus 30.9. What's the solution? 2.915 and minus 30.964. That's not going to fit, is it? Oh, just barely. Okay. 30.964. So if I was being better about this, I would rewrite it. So it's just a little bit easier to see. So we get 2.915 at an angle of minus 30.964. So if omega is 1, we can then tie this, as I sort of said, we're just going to assume that omega is 1 just to make the problem function, to give us something to refer back to. Both of these forms tell us something somewhat interesting about this. So what this one tells us is that the form of IO that we calculate here is 2.915 cosine. Since omega is 1, this is t plus. And so since this angle is actually negative, I'm going to have this be t minus 30. Oops, I forgot the degrees there. 30.964 degrees. And so in reality, we should plug in the radians here, but it is what it is. 30.964 degrees. I was trying to make sure it's still going to be visible when I try to upload it. Okay, so we get a magnitude and a phase. Okay. The other thing that we could do is use the rectangular form. So we could also write this. We could also write this. Sorry. Come on. Give myself just enough space. We could write this using the rectangular form. This is actually, and we generally find this form less convenient, but it is nice. This is cosine of, this is 2.5 cosine of t plus 1.5 sine of t. Oh, sorry. No, the issue is that I didn't write, that's minus. That's how we got a negative here. So sorry, so then this is actually minus 1.5 sine of t. Oh, and I sloped it down and now it's, because of course I'm left-handed, and so of course I sloped it down. So this is 2.5. Try this one more time without sloping down. Cosine of t minus 1.5 sine of t. Pause for a second, have Wolfram Alpha confirm for me that I'm, yep, it's one of those things that I have to wait. Am I sure about that? Okay, 2.5 minus 1.5j. There's a reason for this, but it's actually 2.5 plus 1.5. J corresponds to, so minus j corresponds to cosine of t minus 90 degrees, or t minus pi over 2. If you plug in cosine of t minus pi over 2, it's sine of t. So when you do this trick where we use the rectangular form, that's why I had to double check with Wolfram Alpha to make sure I wasn't messing it up. 2.5 minus 1.5j actually gives you 2.5 cosine of t plus 1.5 sine of t. If this was plus, that would be minus. And it's a consequence of some things, but we never actually do this. And so that's why I didn't have it offhand. I had double checked the. It's because in Euler's identity, you get that sine, right? Sine of t is equal to e to the j. Oh, you won't be able to see this. Sorry, it's because, where can you see? In Euler's identity, sine of t is equal to e to the jt minus e to the minus jt over 2j. So then times minus j over 2. So 1.5, there's a minus j over 2. So when the j is minus, that gives you positive sine. So that's what I was wondering. Is it a direct correlation, or is it because when you do Euler's identity, sine has a minus j over 2 to normalize it and get it to work? Okay. So we can ignore that. And you also don't even really need this form. This is just an aside. And it's more trouble than it's worth to try to remember, is it plus or minus? And so we just write it this way. And so this is the result that our IO says. Now, depending on the value of omega, that's what determines what's in front of the t. But what's nice is we don't need to declare that omega is 1. We know that IO is a sinusoid. We do have 2.915 amperes, and the phase angle is minus 30.964 degrees. The value of omega just determines what is in front of the t. It determines the period of the thing, but we are 30 is about a 12th. It's a 12th of 360. So we're like a 12th of the way into a period shifted right. So from cosine, if you shift cosine to the right by a 12th of a period, 360 over 30, yeah, 12th of a period. So you shift cosine to the right by a 12th of a period, give it an amplitude of 2.915. And then you just, the value of omega just scales the cosine around that fixed point, which is fine. So in the case where we declare that omega is 1, the actual form of IO is 2.915 cosine of t minus 30.964. And so I have just a little bit of space down here. This also tells us a bunch of other things. So we could calculate various other quantities along the way. I'm not going to do them all in the interest of time, but we ended up calculating this value of IO. Now, the other thing that we know is I can declare some voltage here, Vx, across this 1 ohm resistor that experiences IO. And so we can be guaranteed that Vx is equal to IO times 1 ohm. So this IO, it's the leading coefficient that's carrying the amps. But if I multiply it by 1 ohm, then we know that this Vx in phasor form, we know that Vx is just equal to 2.5 minus 1.5 J volts. Well, this was in amperes. Okay, so the phasor form gives us that Vx is just multiplying the phasor IO by 1 ohm. The ultimate result down here is in actual sinusoids, we're talking 2.915 cosine of t minus 30.964 degrees. Volts now. Volts. There's barely enough space, though I'm going to probably have to zoom out. Okay. And you can stop this video at any point. I'm just going to start writing down more interesting results to kind of get a feel for what's actually happening. So I've now determined, so I'm just finding other quantities so that we can get a feel for what this circuit is telling us about the nature of all of these things. So we have a Vx. That's the same Vx that is across these two impedances. So I can define a current here. Let's make it I, Y, I guess. Or well, no, I can call it Ix because I made the other one. The other one is our output current IO. So Vx is still across both of these elements. So we could absolutely calculate Ix also. If we go to calculate Ix in phasor form, Ix is going to be equal to the phasor form of Vx, 2.5 minus 1.5 volts, divided by the impedance between Vx. Vx happens to be equal to V2 just because of the node voltage of the ground node. Use the node voltages, but that is one of the ways we solved it. So we have this Vx. Vx is across this series pair of impedances. So I can calculate the current as the phasor form of the voltage divided by the impedance as a complex number. So this is 1 minus J. Oops, I forgot the J there. Ohms. I'm going to pause for a second and just calculate that with the calculator. Plus 0.5 J. Amperes. So the result can also be written in magnitude phase form. So if I do that, I had it memorized. 13 point, so it's 2.06 at an angle of 13.0, well, 13.04 degrees. And I'll just zoom out very slightly. Very slightly, I guess. Come on, zoom a little more. All right. And now I have more space on the left. So using this phasor form, how far can I go over here? using this phasor form, our Ix is then equal to 2.06 cosine of, again, I'm still letting omega be 1. Otherwise, there'd be whatever omega is right there. And so this is going to be t plus 13.04 degrees. Okay, so that's interesting enough, I guess. Okay, so this is a t, and that's a plus. T. Okay. Okay. So we've got this current Ix. That actually tells us quite a few things now. So we could, if we wanted to, write the voltage Vy across this resistor. We know the currents flowing through it. So Vy, just because we know that's a 1 ohm resistor, if we multiply this current by 1 ohm, we're going to get 2.06 cosine of t plus 13.04 degrees volts, which is the same thing we would get if we multiplied the phasor by 1 ohm. So you just get the same looking phasor, but now it's volts instead of amperes. We know Vx, we know Vy. Now everything should be consistent. If I declare Vz, I should be able to calculate Vx minus Vy. So in the phasor form, Vy would be 1 ohm times this phasor. So Vy, I could actually leave it in the 2 plus 0.5 J form. And we have still the Vx form. Vz plus Vy equals Vx. So Vz equals Vy plus Vx. So I can calculate, or sorry, Vx equals Vy plus Vz. If Vx is plus to minus, Vy is plus to minus, Vz is plus to minus. Okay, we could also use a voltage divider to get there. So the part that's Vz is Vx times negative J over 1 minus J. All of these formulas are then become available. So if I want Vz, I could calculate that as just Vx minus Vy. So Vx was 2.5 minus 1.5 J. And then I wanted to subtract 2 plus 0.5 J. So 2.5 minus 2 is 0.5. Negative 1.5 minus 0.5 is negative 2J. Now there's a 90-degree relationship between, sorry, I just recognized 2 plus 0.5, 0.5 minus 2. There's going to be a closely related angle to, if you take 90 minus 13.04, it's going to be something plus or minus 90 or 180 or something from there. So we can calculate Vz like this. Note there's another important point here, which is that the impedance could have told us that already. Okay, VZ is IX times negative J ohms. So if I had just taken the current IX, which I know to be 2 plus 0.5 J, so I could also have just said, well, VZ is equal to IX times minus J ohms. And sure enough, that's true. IX is 2 plus 0.5 J. And so if we multiply that by negative J ohms, am I running out of space? Not quite. So we're getting there. If I multiply this through, it does in fact equal negative 2J plus 0.5. Okay, so the big reveal at the end of this is, okay, we calculate this phasor form. So I can write VZ. Do I need to zoom out further? No, we're good. So VZ can be written in time as 2.06. So I'm just taking the 0.5 minus 2J. The magnitude is 2.06, and I'm going to snag the angle in just a second. I should be able to mental math it, but I'm not going to do that. Okay, my result says, right, I have to say equals, or it will lose it. Okay, my result says the angle here is negative 76.96. Don't have to look back at the computer because I know. Well, it says 97, so I may have rounded this weirdly. Oh, no, it's because of the separate rounding. I rounded them slightly differently, so when I was doing the calculations, so that's why they don't perfectly match. But okay, minus 76.96 degrees to match my rounding before. It's different by like hundredths of a degree or so. It's fine. So we get our VZ, who has a different phase angle than the current does. So VZ is the voltage in our capacitor. IX is the current in that capacitor. Okay. What's the difference in phase? These are 90 degrees apart, and the currents versus the voltage. Yeah, the current is ahead because cosine gets shifted to the left. So the peak of the cosine is moving slightly backwards from time zero. And the peak of the cosine for voltage is now being pushed to the right. So the current is
Still recording. Okay, sorry. I'm filling in. This is me after the fact, finishing. I'm trying to finish up my voiceover here. Um, so we lost audio on that, so I'm just pausing for a second. So what's happening is, I'm just noting that if we compare VZ of T, um, which is the voltage on this capacitor, to the IX of T, which is the current through the capacitor, we can see that in this case, actually I'm going to stay in green. In this case, we can see that the voltage waveform with its minus 76.96 degrees is delayed by 90 degrees from the current. So the current is a cosine, but we shift it left by 13 degrees. And the voltage is a cosine shifted right by 76 degrees. And so that means that the peak of this cosine hits 90 degrees before the peak of this cosine. And so since this is a capacitor, when the current peaks 90 degrees before the voltage, which is the ICE mnemonic, if it was an inductor, we would expect the voltage to lead the current. Okay, and I kind of worked ahead by writing this. This is the next point I'm going to make, but here it's just that in a capacitor, we see the voltage leading the current, or sorry, the current leading the voltage here, because the current peaks 90 degrees before the voltage does. Okay, I'm just going to continue the audio again.
Leading the voltage by 90 degrees. So the current is leading the voltage by 90 degrees. This is a capacitor. And so current in a capacitor, current leads voltage by 90 degrees. For an inductor, the voltage should lead inductor, voltage leads current. But in capacitor, current leads voltage by 90 degrees. 13.04 versus minus 76.96. So that's almost the big reveal. And so the big reveal that I wanted to end this video on is to note that this idea is going to be consistent with the current voltage characteristic in a capacitor. So in a capacitor, I'll zoom out one last time just to give myself a little bit more extra space. Actually, just point it downward a little bit. So in a capacitor, we know that IC of T is equal to the capacitance times dVc of T dt. Vz is that capacitor voltage, and Ix is that capacitor current. They are consistent with the passive sign convention, so the differential form holds. So we know the form of Vc of T, it's the Vz here. So we know that Ic of T needs to be C dV dt. And so that's why I checked that if omega is 1, C is 1 farad. So C is 1, and then dVc dt, I'm trying to take d dt of the Vz. And so I'm taking the phasor, turning it back into a regular sinusoid. So this is 2.06 cosine of T minus 76.96 degrees. Okay. The derivative of this, the derivative of cosine is minus sine. So this should be equal to 2.06 negative sine of t minus 76.96 degrees compare that to what the current is known to be from the phasor form. The phasor form tells us this is 2.06 cosine of t plus 13.04 degrees. And so I am desperately, desperately hoping that minus sine with a phase of 76.96 degrees is the same as a positive cosine with a phase of 13.04 degrees.
So I'm actually going to chop the next thing that I did because I took forever. So if you plug these in, if you plug these two forms into, if you plug these two forms into Wolfram Alpha, you'll see that they are in fact the same. You can also use the transformation table that I showed. But what we can tell is that if you take minus sine, and then since the phase here is a minus 90 relative to the cosine, what this is saying is if you take negative sine and shift it to the right by a quarter period, it should be equal to cosine. And so if you graph negative sine versus cosine, if you take the negative sine graph, move it 90 degrees to the right, it will match up with cosine, or you can just plug it into Wolfram Alpha. So I had one more closing note, I think, so I'll let my recording come back in just a second.
That's sort of some background. We're checking these complex numbers. The value of the complex number in phasor form tells you the magnitude and phase of the various currents and voltages in the circuit relative to a base cosine of amplitude 1 and a cosine with phase 0. If your number is purely real and positive, that corresponds to a flat out cosine with no phase shift. So you get in the complex plane, you get a magnitude and a phase that corresponds to the magnitude and phase of the cosine. So when Vx specifically, so if we start here at our, so we look at our Vx, the complex number for Vx is 2.5 minus 1.5 J. The magnitude of this is the magnitude of the cosine voltage, and the phase in the complex plane is the phase shift of the real voltage waveform. And everything is consistent with the derivatives that we get. We calculate impedances by taking the ratio of a voltage phasor to a current phasor. We do this for a capacitor, an inductor, and a resistor of fixed capacitance, inductance, or resistance. You put a sinusoid of arbitrary phase and frequency and amplitude, take the ratio of the phasors, and you obtain the impedance formulas for the various elements. So ZL is J omega L when you take derivatives. ZC is 1 over J omega C after the derivatives, and ZR is just the real number R, the value of the resistance. And so there are already videos where I talked about those, but I wanted to show that these phasors, that the complex numbers are just a way to allow us to algebraically manipulate AC circuits in the same way we do DC circuits. So instead of all of our numbers being purely real, they are now complex valued. So instead of being purely real, they can be either positive or negative, and that's it. Once we extend to complex numbers, the magnitude describes the size in the complex plane. The magnitude in the complex plane describes the size of the current or voltage, and the phase of the complex number in the complex plane describes the phase of the AC waveform relative to a direct cosine with no phase that is maximum at time t equals 0. So if your current or voltage has a phase angle of 0, it is at the magnitude value at time 0. If this has some other phase, the phase determines how far to one side or another the peak you reach the magnitude. And that's all we're actually trying to do. So it's not trivial at all what we're doing here, but hopefully this somewhat clarifies. I've tried to be really careful and set it up so that I'm constantly checking my own answers, so that if I get something inconsistent with what I expect, I went back and took another look at it. And so it appears that everything is okay, or at least but then everything did seem to hold up. Because I showed that the voltages and currents in this zone are all consistent with each other. We found Vx, Vy, Vz, the current here, and they were all consistent with KVL and KCL and Ohm's law using the complex values. So it's still a lot, but I figured it would make things slightly clearer after we do this. So